We're going to be looking at a design exploration of 1678's 2019 robot. But before we dive straight into the robot, I want to look at a couple ways that we can start looking at other teams' robots, and when we start needing to find designs and things, if we know we have some video from the past or some robot we want to look at, how we might be able to find information about it. So one of the first places that everybody should know about is the Blue Alliance. You can come in here and get pretty much all of the stats and data on like match wins, and a lot of videos from all the matches, a lot of pictures from robots, from pretty much every team back through modern FRC history at least. It gets pretty sparse as you get towards the early 2000s and into the 90s. But everything modern has a pretty good update of where all of the teams went and everything like that. So if we're going to look at Citrus's 2019 robot, we can start by seeing some of the photos of it. There's definitely some complications going on. It doesn't look like a normal robot necessarily. It has some wings. It has a lot of things. The 2019 game was kind of complicated. And we can look at how some of that worked and how the game gets played. So yeah, so seeing photos is useful. So if you just need to glance at something, you can do it there. Sometimes, depending on what it is, they'll have more photos at the bottom. They're not always at the top. So you sometimes have to scroll down because you also have videos as well. So we can look through and see some of their the action of the robot and see how well it works. So yeah, so we can see it doing, oh, that didn't work. Hold on, I messed up somehow. Let's try that again. That's better. Yeah, so it has the elevator, has the big arm that swings all the way through, grabs balls below and hatches above. And then this is the other part of this robot that no one else could do reliably, was they could lift two other robots and climb onto the HAB3 platform by itself, which was very impressive, and no other robot was doing that feat in that game reliably. There was like one other robot I think did it a couple times in match, but they were able to do it almost every match and got it consistent, which was really impressive. Okay, so it doesn't have a specific CAD link here or anything. A lot of times with some teams, especially the more well-known ones, most of their stuff is going to be linked on their website. So a lot of times we can find it in here if you go to like resources and you can look through and see their other ones. So here's their 2019 robot, 2019 Buzz. We can read more. And normally they'll have some links to things. I don't know if they actually have the CAD in here. Maybe not. So yeah, so you can read about it. You can see different mechanisms. They have different renders. But the other place where if you just want to look at CAD of a lot of robots is we have our CAD collection at spectrum3.47.org. And it's a sheet we set up several years ago, and now it's easily maintained. We just, whenever people submit, we just add in the links to update it for different years. So it's basically just a big Google spreadsheet that has a lot of CAD that you can go through and look at from robots from all over. So if we want a specific robot, we can scroll through and find their team number of just everything, but we can also go through the year list. So if I'm like, okay, I know it's in 2019, I can pull up and scroll down and find 1678 from 2019, and they're on here. So then we have a link to their Onshape document that you can just load up as long as you have an Onshape account, and you can look through a lot of teams' robots this way. So there's a ton. Some of them aren't Onshape. Some of them are like step files, which you have to import into Onshape to view. You can look at Onshape direct ones here. These are all the Onshape robots that are just direct links. So if you don't want to import anything, you don't want to take time, you just want to look through robots, this is a really great way to start learning how different teams build mechanisms and how they accomplish the different tasks from all the past games. So especially once we get the new game, we'll start discussing pretty regularly whatever game is the most similar to the 2023 game. There's been enough FRC games now. We're 30 years into this thing. There's probably some past game that has mechanisms that are close. And so maybe it's elevators, maybe it's frisbee launching, something, who knows. We'll probably be able to find examples from past robots and look at them. Some of them we have to research more because they might not be on here because they weren't as modern, but we're normally still able to find some examples. Okay, so we're going to look through Citrus's robot tonight as it loads up in Onshape. And so it's set up currently with the kind of in its expanded state. So it has its manipulator up here for the cargo and hatches. The balls that year were called cargo. And then this mechanism down here is part of the climber assembly. So we'll be looking at that in a little bit. So normally this whole stage was sitting down below, kind of just right on top of the chassis. When they weren't climbing, it was all folded up and down there. And the only part that moved up and down on the elevator the only part that moved fully up on the carriage was this main mechanism, and then this is actually mounted to the front stage. But we'll look at that in just a second, how that all works. Okay, so with most robots, we can start by looking at their drivetrain. That's kind of how we kind of base the rest of the robot on it. A lot of the other design decisions and how they do things are going to be based on what drivetrain they're using. Pre-2022, there were far fewer swerve robots in the world. So most teams had some version of a tank drive. Citrus was known for building a very standard, what's considered a West Coast drive, where they have a frame rail right here, and they have these wheels sticking outside of it that are cantilevered, which means they're only supported on this one side, right? The shaft is going through this wheel here, and there's no other tube or plate or anything on this side, right? This is just bumper. This isn't supporting the wheel at all. So if you pull the bumper off, you can very easily swap the wheels out just by taking off whatever's retaining them. In this case, this little groove right here is for a snap ring. So there's a little piece of steel loop that's a little snap ring that goes over that groove and holds the wheel on. And so that's kind of your standard definition of a West Coast drive, is you have the 2x1 tube rail on both sides, 6, sometimes 8 wheels, and they're cantilevered off the side like that. There's a few different other ways you can do them. So in this case, to power all the wheels, this model right here is for the chain. So there's chain to each of the, that got weird. Let's see if we can see it from the other side a little better. So there's chain to each of the wheels from the middle gearbox. So back before we had a large amount of brushless motors, so 2019 was the first year we had brushless motors at all, so we had Neos for the first time, but a lot of teams still weren't using them. For a variety of reasons. They were brand new. No one knew how well they would work or anything. And so it wasn't like every team was using them yet. So if you didn't, the kind of standard drivetrain before that, between like 2016, 17 up to 2019 for most teams at kind of the higher levels, was a 6 mini sim drive. So you'd have 6 mini sims powering your drivetrain. For comparison purposes, a single mini sim is like probably a little over usable, like half of the amount of like power that a Neo or a Falcon can give you, the modern brushless motors. Roughly around 200 watts, and the Neos and Falcons are roughly around 400 usable watts. Those are very much approximations. But so you can imagine, just by going to 4, which is what we have on our swerve drives and what we ran in 2020 on our tank drive, you still have more power than 6 mini sims. And these were a whole lot heavier. Each one of these is a lot heavier than any of the brushless motors we have now. So that made your weight budget a lot harder because your motors were so much heavier. Okay, so yeah, so the rest of the drivetrain is pretty simple. They just have a pinion gear on the motor going to a large gear. So this is what we call a single reduction drivetrain, where they just have this one gear reduction here to change the high speed spinning drive motor to a lower speed that can actually have enough torque or rotational force, basically, to be able to push and drive the robot and accelerate better. You would never want to drive an entire robot with just directly off the free speed of any of the motors. They spin way too fast. Yeah, so then this gear has a shaft that goes through, powers this middle wheel directly, and then the chain goes out to the 2 outer wheels on each side. So it's a really basic, simple reliable drivetrain, which is why they were able to use it every year and do very, very well with it. There are a couple useful things. So in this drivetrain, the plates here, they have these large standoffs. Let me see if it has the, yeah, so you can see they have a couple little tubes on the inside there to like center them. But those larger tube standoffs are nice. They allow you to clamp a lot harder, and they put a bigger surface area, so you can't have any flex or anything between those plates. So especially on some of the gearbox ones, if you can make a larger standoff instead of just using like a 1/2 inch round or a 1/2 inch hex like a lot of teams will do, if you can go and get something bigger, we can see what this is. So this is up at 1 inch. This is a full inch diameter tube that they're using there. You can add a lot of stiffness when you bolt through that as your spacer. So there's some times where you want to use a bigger one. A lot of times we'll use the 7/8 tube that we use for a roller and for a lot of other things, just because it's a pretty standard material that we use a lot. And 7/8 is close enough to 1 inch that you're getting a lot of the same benefits. But then there's some other times where you might not have the space or you don't need it as much. So coming up here, they put some smaller ones. Since this isn't these aren't actually mounting anything into the rail or anything or supporting the plate as much, they're just using smaller standoffs to keep the space down when they have to get closer into the gears and the motors and everything else. Okay, so the rest of the chassis is just 2x1 with the hole patterns drilled into it. So in 2019, they were doing this all themselves. They were doing this on a router most likely, the same way that we made all the tubes for like the robot cart. Now, for most of what we'll be doing, we'll be using Rev Max tube since it comes pre-drilled, and we won't have to spend the time doing it on the router. But a lot of their build techniques will work the same way with Rev Max tube, since we can make the same sort of gussets and construct frames in similar way. It's going to change a little bit because we're doing swerve, but the kind of basic idea is still there for how the frame's going to work. The rest of their, so the rest of their drivetrain is just those 4 2x1 tubes going around it. They do have a diamond cut, whatever, water jet, laser cut, however you want to do it. Belly pan is pretty standard on a lot of robots have done things like this. Basically, they use a relatively thick piece of metal. So this is 0.09 thickness piece of aluminum normally, and they cut it down so that they can still keep some of the stiffness but lose a lot of the weight. And if you have a sponsor who can do this for you and is willing to do it, it's completely fine. But it is rather expensive and time consuming to do all the cutouts. So most of the time for our robots, we just use plywood, but this is definitely a completely acceptable way and has been a pretty standard design method for a lot of robots for many, many years to have this kind of diamond plate. You still keep a lot of the stiffness across the chassis to make sure that your frame stays square, so all of the corners stay at 90 degrees to each other. You have all the places to mount your electronics built in, or they add in all those holes. But most of the time, for most of what we're doing, we don't need to go to this extreme. It definitely takes longer to CAD and develop. And if you have enough people and you want to do it and it works for your design process, it's fine. Most time for us, it's easier just to use a piece of Baltic birch, which is going to give you probably a little bit more stiffness if you leave it fully done and you don't have any of these places where the sheet can flex. And we go to a bigger thickness since it's wood. We go to about 1/4 inch, and it ends up being about the same weight for a lot less manufacturing time for sure, and some less development time, because we can just put it on our laser and make it really, really fast. Okay, so the other parts of this are, let's see, so they have their couple things that may not be completely obvious. They have these little poles out here. So these are for backing to the bumper. So there's a bunch of bumper rules about how your bumper has to be secured to your frame and where it can be touching, or how far away it can be from the corners in here and things. And so to get in compliance with all those rules, they have these little plates that are sitting behind the bumpers here that mount into these tubes. So they do that on all 4 sides. And then they mount standoffs going from here to these large 3D printed parts, which we're going to look at in a little bit. And so this allows them to back the bumper entirely across this gap. And they have it backed by the frame on this other side so that they can meet the bumper rules. So there's going to be some things on our robot that we do the same thing with, just to make sure we're in compliance with all the bumper rules. There's some things that we sometimes have to add little bits of material or different parts just to make sure we're fully in compliance with the rules. Okay, so yeah, so I think that's most of the drivetrain. We'll get to endgame and climber probably towards the end, so we'll look at the elevator next. So in here, these main two uprights are the stationary uprights for the elevator. So we normally consider elevators to have stages, and it's a little bit confusing sometimes depending on what people say. They'll say that an elevator has two stages because you normally have two parts that move, but then like trying to name these outer ones, or like the uprights, the part that don't move, giving those a name gets confusing. Every once in a while someone will call those the first stage because they're like kind of part of the first stage. They interact with this other part of the stage. So the nomenclature gets a little bit weird. If we end up designing an elevator, we'll set up terms so we try to use the same one so everyone knows kind of what we're talking about, because they're not always easy to know exactly what parts of the robot we're actually naming. Most of their stuff's all in part numbers, so we don't get any names from them. But yeah, so these uprights are what taking is the only place that the actual elevator and all of the mechanism things are mounted to the rest of the robot, so this all needs to be pretty strong. So they have some big gussets down here mounting in those tubes to the main frame rails, and they have an even larger gusset on this outside plate doing the same thing. So this is probably a 1/4 inch aluminum plate, or something along those lines, 3/16, so 0.188. So this is a pretty big aluminum plate that's going to make it to where this tube can't move easily in relation, because the whole robot's going to be lifted off of this stuff, and you're moving up and down to do all the scoring, so you want to make sure that's really secure. They have quite a few rivet holes in here and through into the main chassis as well. And then in addition to that, because you do have a lot of different forces coming on this, once you're putting it up there, you might be running this into you might be running it into like the rocket or something when you're actually scoring, or just the amount of weight up there, it may start shifting if you're accelerating, anything like that. You do want to have some sort of angled support to sort of make this big triangle that's going to allow for your uprights to stay vertical and not flex back and forth and move around on you. So they do that with another piece of extrusion here and a few different gussets to mount to the uprights, and then down to the frame. Yep, there we go. So there's the gussets in there to mount to the frame. And so that lets them keep everything mostly vertical, as most as they can, on the actual elevator itself. Okay, so that's most of the structure for the elevator. Oh, the last part we can talk about is the keeping it across widthwise. So if you just have these uprights and you don't have anything crossing, which is what this tube does, it's easy for them to potentially want to move the other direction, left and right. So you might have this tube want to come outside or bend inside, and you don't want that either. So most of the elevators are going to have some way to cross to like have an entire cross member at the top to try to keep those rails square to each other at the top, since they're not mounted securely like they are at the bottom. And so that's what this rail up here does. So the way they do that is they have these outer plates, which we'll look at in a little bit because they have some other purposes. But they have these they have 4 holes in here. If we hide this, we should be able to see a block on the inside here. Yep, so we have a 3D printed block that has these like nut pockets in it, so they can put nuts inside of there. And they can mount to those side plates, and then also mount through this block into this block and all the way through into the tube on the inside. So they're able to secure this all the way through and mount up the side plate as well. And so that's how they're able to fully secure this cross member. And while we're up here, we can look at this is also where they have their limelights mounted. So this is for their vision system. So they have 2 different limelights mounted here, so they could track the targets in 2019 and align to the goals the way they needed them to. This is another good use of 3D printing. So they have these cool 3D printed brackets that encase the limelight like that, which is a pretty nice way to do it. And they also have this little shield that would have been mounted up on top of it so that if anything, part of their elevator or anything else came in, it wasn't hitting the limelight directly. So they had this bent piece of Lexan that they could bolt up through the sides of it that they probably added at some point to help with any sort of deflection. Likely when the arm was coming through, in case it didn't quite, if they didn't get something right, because this part can swing under, they probably didn't want it to crash into the limelights directly. This way they can hit the Lexan first, hopefully. Or also any of the balls or anything else, other robots possibly getting in there. It would have at least helped a little bit. Okay, so yeah, that's the main structure. So let's look at the bottom of the elevator, and then we'll work our way up and look at how all the cables are routed. This big gearbox down here, so all of this, so these tubes, these 4 motors, so again, this is before we had brushless motors, so these 4 motors, these are called, these are 775 sized motors, so these are either 775 Pros or Andy Mark Redline motors. And so they have 4 of them on this gearbox. They were driving the elevator and their climber mechanism with 4 motors to be able to have enough power to lift not only their robot, but 2 other robots at the same time, right? So they're lifting potentially somewhere in the neighborhood of 450 pounds, pushing it up the 30 inches, 36 inches, 24 inches, 20, somewhere like that. I don't remember, 2 to 3 feet, I believe, in the 2019 game, and driving it onto that platform. So they needed a lot of power to be able to fully lift that much weight that high and still drive forward, which we'll look at in a little bit how they do the driving. So this gearbox has those 4 motors here. You can see that the gear teeth are different sizes. I think we've discussed that a little bit in the past, but this is because you have different, what's called pitch on the gears, which is the distance between each tooth. Most of the time for us, we're almost always going to use 20 DP gears, which is what all of these gears are here. The smaller pitch, which we still have on a few different places, still have them on like the MK3 swerve modules on the prototype robot, and the 2021 robot uses these in a couple places. There's a few more on some of the old robots. And these are 32 DP, and they just have smaller gear teeth, and you pretty much only use these as like the first stage of a gearbox, where you have the motor going straight here, and then you have some other gear after it. If you tried to drive something with a lot of power here, you could break these teeth a lot easier than you can the ones with the larger teeth. So most of the time we're going to use these 20 DP, and there's even times where you might need to go bigger than that, and there exists in the market, and some teams have used 10 DP gears as well. So you can go all the way to about double these tooth size. So if you have something that has a lot of load on it, or you need to be able to machine it easier, because it's a little hard to machine these 20 DP gears. So if you wanted to make like a big turret ring or some other big gear for an arm or something, where you might have to be like laser cutting it or routing it, doing it out of 10 DP works for that really well. Okay, so yeah, so we can look at this gearbox. This may be a little confusing at first because it has 2 gears both on the same 2 shafts. And normally you would never want to do this because this would mean the shafts are spinning at different rates. But they do that because this is able to shift. And I don't think we've talked about shifting much this year because it's not nearly as useful anymore now that we have brushless motors. Pretty much everyone can put a lot of power. Just by adding another motor, you have more power than all 4 of these combined. So you don't have to shift as often. But what they are able to do is they basically have this pneumatic cylinder right here coupled to this little shaft. And when it moves in and out, it moves this piece here, which is called a dog. I don't know why it's called a dog, just know it's called a dog. It's called a dog, and it moves back and forth, so it normally has a little screw. That screw goes through this shaft. It's not CADed exactly right. And then when it's engaged in one side, these little teeth here engage into the side here, and now this shaft is rotating with this gear, and if you push it the other way like it is here, these teeth engage into this side, and now this shaft is rotating with this gear. So you can go from having the entire elevator geared slower when you have this reduction here, when you go from small to big, you get that reduction, so this shaft is spinning slower, or you can have the elevator spinning faster by going to these 2 gears where you have similar sized gears, so you're getting something closer to 1-to-1 or 1-to-1. know the exact teeth count here. And so you can see that you have a high speed and a low speed. So during the actual match, when they want to move the game pieces up and down really fast to be able to score on the rocket, they're going to use this high speed side. And then during the end game, when they want to be able to lift a lot of weight, they're going to use this low speed side to be able to have a lot more torque from being able to reduce your speed by so much. Okay, so then that, whichever two of those get powered on that shaft, you have another shaft here, you have another gear set here that does some more reducing, and you have your final reduction at this outside where they have two different gears driving this shaft, or driving these two shafts, actually, these two drums separately. They should be in sync with each other since they're driven off the gears, but it's not one continuous shaft because the shaft in the middle here doesn't actually spin, right? So these drums are spinning on top of this shaft through the middle, not spinning together, just linked by these gear teeth. And that's important because sometimes the gear teeth aren't made the same way. So if this gear teeth doesn't line up with the hex the same way, and you try to put two on the same thing, it wouldn't work as easy. And sometimes they'd be misaligned. The new rev gears are keyed to the hex shaft, which is very convenient. It means you can put multiple gears on the same two hex shafts and basically just like make a gear extra wide if you want. So by adding extra width, you make it so you have the same amount of force transferred through less of each portion of the gear tooth, so it's less likely to break a gear tooth. So if we need to have a lot of torque transferred, we can use the new rev steel gears, stack them up, and you can have, instead of a 1/2 inch wide gear, you can have an inch wide or a 2 inch wide gear running if you really want to. Okay, so what these things do, and the CAD makes it a little bit trickier because in real life the ropes are wound and things, it's a little bit easier to see. But basically these drums here allow you to wind the rope, that's kind of shown here. So this is all the rope path here. And this is how you actually move the elevator up and down. So they get wound around this drum. They go up over this pulley up here. So we have a pulley right here. Then they come down. And this one comes down and attaches somewhere. This is probably attached to the carriage or something like that. The other side gets a little bit different treatment, or maybe the similar treatment. Oh yeah, so this would go up over the pulley and mounted into, I guess they both get mounted to this stage is what it looks like. Let's see. So yeah, so that goes up there. This whole stage would be further down, so these look like where the mounting points would normally be. So they have where you have those little loops here, would be where those would mount up to this stage normally. So it's not done quite perfectly in CAD, but you get the idea. And they have a couple different ways that they can tension that rope. So they can turn this turnbuckle. So as they turn that, these two eyelet bolts get closer together so they can add tension to the rope. And then they also have a spring involved so that if anything changes in the rope tension, a lot of times if you're going forward and backwards and as you're doing stuff, it might need to stretch a little bit. So they have a pretty strong spring probably there that allows the rope to move some if it needs to, but most of the time it's going to be pretty tight and allows it to keep the same amount of tension as it's moving up and down. I'm not sure what the carriage stringing is on this robot. It looks like there's another rope here. Oh yeah, so there we go. So there's the, here's the front for where the carriage is. So this is actually not a, from the look of it, I believe that this is a cascade elevator. There are two different types of elevator wiring, or like rope stringing type things that you can do, ways to rig it so that how the motion works. This appears to be cascade. We can go back and look in the video and probably get proof of that. And what that means is basically the carriage, which is the last moving stage, normally wherever your manipulators and stuff are of your elevator, this part right here is called the carriage, and it's tied to the movement of this first moving stage, and then that's the only part that the actual main elevator drum is moving. We'll go into more detail on that. We'll talk more about elevators a little bit later and compare the two, because that's a whole presentation on itself. But knowing that it's Cascade does help know a little bit about how certain things are going to work with it. And we can look at the video and kind of prove some of that. But basically, when the arm is fully down, everything is down. But as soon as you try to move it at all, both this stage and the carriage are going to start moving up at the same time. So this is going to always stay the carriage distance from here down to its bottom point on this first stage is going to basically be the same distance from this first stage to the stationary elevator down here. And these are going to stay the same as they move. So as one gets an inch bigger, the other one's also going to get an inch bigger. So if you wrap this string a single inch, if you move it an inch, you actually move the whole elevator 2 inches because of the way the Cascade works. And that has some advantages. You get some gearing advantages here. So you can be, this first stage moves half the speed as the overall elevator does. So you end up getting some more torque here, which is helpful for the climb mechanism compared to the manipulators up at the front. Yeah, and so they did everything with string. You can also use chain for elevators. That's what we've done in 2019 and 2020 for our climbs, and for our elevator for scoring in 2019. You can also use belt, so teams can use timing belt. Teams have used different like strap, like the same type of strap we used on the climb in 2022. You can use different types of rope. So there's all sorts of things you can use to kind of get that linear motion for an elevator. Most of the time with something like this, if it's modeled as round cord, this is probably what's known as Dyneema or Spectra cable. It's the same stuff we were using that we switched our 2022 climber to in for NTX. But this is thicker. This is probably 1/8 inch diameter or something like that. Maybe even bigger. Yeah, this might be, I don't exactly know what this is, but it gets pretty big. Depending on what they're using, and this can take a lot of loads in the thousands of pounds as you get thicker in this stuff. So it's an ultra high molecular weight polyethylene. It's a full synthetic cord. It's not like cotton rope or anything like that. It doesn't stretch a lot. Like, you still need some work to tension it, but it doesn't have to be as much as a lot of other rope that would stretch a lot under the loads that we put them in for an FRC robot. Okay, so that's kind of how the motion works for the 2 stages of the elevator. I'm going to skip the climb and come back to it so we can look at what the carriage looks like and how they actually score game pieces. So in here, oh wait, I actually missed one thing. Take it back. We're going to look at the bearing assembly on the first stage real fast. So elevator bearings, and we'll go into more of this. We'll probably have another day on elevators. But you basically need to constrain the elevator with bearings on all 4 sides of each stage. Otherwise, it's possible for it to move around. Either you have rolling bearings, like actual ball bearings like they do here, so they have a bearing here and here, or you have, sometimes you'll have just a surface where it has reduced friction that is just sliding again. So some teams will use plastic, and you'll just rub against the plastic, which a lot of times in this side-to-side motion, so you have your, these bearings here, if you replace those with plastic, it's normally not so bad because there's not a lot of forces trying to move the elevator side to side, compared to front and back, where you have a lot of weight hanging off like the front of this elevator here, so it's almost always trying to lean forward. So you want to make sure that these bearings are working the way they're supposed to, and it's less critical to have them on these sides. But if you can have roller bearings everywhere, that's the better way to do it when possible. There's a lot of different elevator kits and things now that exist. ThriftyBot just came out with a new one. Andy Mark has one. West Coast Products has kits. So there are kits that are available to do this and get design ideas from. We're prototyping ours right now, or a version of one that we may use. So there's a lot of ways to do these different bearing setups. and kind of dialing them in to get them right, because you have to leave enough room. You wouldn't want this to be exactly 2 inches to where it starts like binding, but you don't want to leave too much room to where it can wiggle. So there's a lot of little things you can do to mess with the tolerance and stuff. In here, they don't have everything CADed, so they're definitely, these bearings just don't float clearly. There would be a bolt going all the way through it, and then spacers in between them, holding everything in place. Same with across here, there'd be a bolt going through it, and some spacers putting it in the right spot as well. And so that happens at the top of the stationary stage and at the bottom of the first moving stage as well. So you have these bearings here that would be bolted across these plates. And on the inside, this is getting harder to see. Let's see what I can do. I can hide this. There we go. And then you can see here they have some cutout in the tube where they have the lateral bearings for this stage down here as well. And so that works pretty well. And they also have oh, yeah. And this is the bottom pulley for the upper stage. So this bottom piece of rope here would stay on this pulley all the time. It would stay there. It just doesn't do it in CAD at the moment. And then you also have things like this. So this little block here is how the rope gets mounted. So this would get, the rope would get routed through this block somehow. And that would keep that bit of rope stationary. And that's how they're able to transfer the motion. They have the rope stationary here, and they should have the rope stationary somewhere on the carriage. Yeah, up at the spring here probably. So it's probably tied here and then tied here. And then the rope is able to move up and down the carriage as the distance from this central tie point changes to this pulley. That changes the distance from these two tie points to this lower pulley as well, and that's how it moves up and down. So this is for sure a cascade, just using rope to do it instead of chain or strap or anything else. If we look in here, we can kind of isolate this and see what it looks like. Yeah, so it has some ways for the rope to go through. They're probably just winding the rope through this path somehow, and then bolting it down with these bolts. And that makes it so it's completely locked and gets fully clamped, and the rope can't slip through it at all in case once it gets enough load on it. All right, so back up to the carriage and their actual game piece manipulators and everything. So the carriage has a similar bearing assembly, but it's kind of done on flat plates. So they have these 3D printed blocks here that are kind of cool. Let me isolate this. So these get printed as one part that has the holes to mount the side bearings through, and then a inner holes to mount the lateral bearings. And so they actually push a pin, just like a dowel rod, through, and that has these bearings on it. So they'll put those bearings in and then push a rod all the way through and then capture it somehow in there. It may just be pressed in. I don't know if there's anything holding it. There's no real force trying to slip it in and out. But those are cool, and those are done on the top and bottom, I think is what I saw. Yep, so you have them on the bottom on each side as well. And again, there'd be bolts going through this and holding everything together. So this is a nice simple way to do a carriage with a single printed part and a routed sheet that you can then do a lot of your mounting to for the actual movement of like the wrist here. So this whole thing's able to flip up and down. It's actually able to flip a full 180 degrees, so we can go backwards for hanging the hatches backwards if they need to. And they're able to integrate the wrist gearbox into this other side plate. So this is how they're able to get motion here. They have another one of those 775 motors mounted here with more gear reduction to a chain and sprocket assembly. So anything like this where you have a slow moving joint, right? This isn't spinning really fast. This isn't like our launcher that's going to be spinning at high RPMs. This is spinning pretty slowly. You want to have something like chain instead of belt, as the chain's going to engage and be able to transfer more torque normally than most belt setups. Like you'd probably make a belt setup that did it right, chain is just going to be easier to do in most cases. So they can start with gears here to get the reduction they need. You could also do something like a planetary gearbox. The Max Planetaries work for this, or the AM Sports. And then go straight into the chain if you didn't want to build up a gearbox yourself. Just kind of depends on space and weight and what motor you're using to determine how you want to do that. This extra sprocket in here is an idler or a tensioner, depending on what you want to call it. And so this slot that they built into this plate allows them to have a bolt running through this standoff and through this sprocket, and they can start it up here kind of out of the way, and then if this, as this chain potentially gets loose, they can loosen that bolt and slide it down and get it to where it's putting pressure on that chain and tensioning the chain as much as they need. It also, you could do it the other way and you could have it pull up. I'm pretty sure this setup is designed to pull down, but you could go the other way and push up and push out on it. But if you push down, you get more chain wrap, so more of the chain is engaged with each tooth on the sprocket, which is ideal and better than going the other way and pushing it up, which means like this thing's going to move further away and you'll have less of these little teeth engaged with the chain at any one time. Depending on what you're doing, either might work. Getting more wrap around a pulley or around a sprocket is normally better, especially if you're trying to transfer a lot of force, where you're moving something like an arm or a wrist. You can be better off with more chain wrap. Okay, so yeah, we already talked about that being there. That's where the rope ties in. Oh, actually, this might be a chain tensioner too. I'm not sure. So yeah, it looks like this hex shaft is here and can rotate. So it's very possible they do something here that allows them to spin this and spin up some of the rope here to be able to tension it. So you can wrap rope similar to what we used the wrench and ratchet here for on our 2022 climber, where you put a ratchet on like the end of the shaft or on the inside of the shaft, and as you spin it, it can wrap some of that rope around the spool here, and that'll take up any leftover rope in your big loop, and you can keep everything tensioned that way and do that well too. Okay, so yeah, we looked at the gearbox. We have this big sprocket. It's mounted to this tube. It's very possible, they don't have the sprocket modified in CAD, but let me see if the block shows it. Yeah, so you see this block, how it has all of these holes here? It's very likely that this isn't something they did in CAD, but it's very possible that they drilled a lot of those holes into this sprocket instead of just relying on the few, like the 6-hole pattern that is already in it that comes stock in a lot of the sprockets. A lot of times you'll have about 6 holes, depending on where you buy the sprocket from. But they're all pretty close to the center. When you have this really big sprocket, ideally you want to have some mounting points further out so you get that bigger lever arm. So as the sprocket's moving, it's pushing on a bolt here and it's taking like the load further away from the pivot, which allows it to just lift the arm easier. It would probably work with the bolts here. You just put more force on each of those bolts to actually keep everything connected than if they're further out and have that bigger lever arm to the pivot coming in. So that's why they almost certainly drilled some of these holes out into the sprocket and then bolted in that sprocket in through the tube or riveted or something else to get that connection there that wasn't going to break. Okay, so what else do we have here? We have this post, and so this post going all the way through is the axle or the pivot for the actual arm. So this sprocket isn't mounted to the shaft at all, right? So this this piece right here is called a bushing, sometimes a plane bearing, and all it is a very smooth, normally piece of bronze or sometimes not bronze colored because it has enough steel and stuff into it where it gets silver, but it's normally something like that. And the way they make them, they're actually self-lubricating, so as you rub against them, they have some different properties that allow material to slip against them well. So you normally have like an aluminum tube here and this bronze bushing that when you're not spinning at high speeds, again, this isn't a launcher, this is only spinning a few, maybe 180 degrees in half a second, whatever it is, not doing tons of revolutions per minute. You don't need a lot of roller bearings, and they can take a lot more force, and they can package a little bit smaller onto a bigger axle. And so we use things like this pretty regularly for any slow moving joint that's going to have a lot more force on it and need to be able to be a lot stronger. We'll use plain bearings or bushings, depending on what you want to call them. And we have quite a few of them in stock in our lab, but we also can buy them from places like McMaster. They're a pretty standard part for a lot of machines and things. They're not really an FRC specific part, but they work, and a lot of people design them into FRC robots. So this shaft again is a what's called a dead axle. So the axle itself doesn't spin, so only the arm and the sprocket spin. So this is going to have, almost certainly because of the way it's done in CAD, this is probably going to have a threaded rod going all the way through this. So there'll be a threaded rod going from this hole all the way to this hole, and then you have nuts on both ends that are just clamping this plate to this plate very securely. And so you can tighten those down, you can clamp across this whole rod, or this whole tube, and get a really strong, rigid structure across those two plates by having that threaded rod clamped down and secure. It also makes potentially changing it relatively easy. You can just take that threaded rod out, unscrew it, and now the whole mechanism, this whole inner mechanism here, once you undo the chain, you can probably just drop it down and take it out without even moving the chain, can come completely out, and you can work on it, you can replace it, anything like that, which would be very effective. You probably have to deal with some of the wiring out to the motors that are out here and some of the pneumatics, but you could definitely do maintenance on it pretty easily. Similarly, on the other side, they have a couple more bushings and some extra gussets here. There's a few little detail features that are really important in a lot of robots that get overlooked a lot of times in design. So this right here is a magnet mount. So they made this little 3D printed part. So this is almost certainly printed, right? You can imagine this was flat to the printed base, and then everything else was printed up. Anytime you have this kind of like organic-y shape, they almost certainly didn't cut this out of a big piece of aluminum or anything, so it was probably printed. They have that it lets them get the magnet in the right place to be able to come over and be able to activate this sensor here that can detect when the magnet is in front of it. So that lets them know the position of the arm and not have it go down any further, right? Because if the arm kept going down, it would run into this rod, and they don't want to do that with a lot of force. So once the magnet's in front of it, it signals the control software to stop the motor, or to at least limit the power to only hold it right in this position. So this is another very good use of 3D printing. They have some little spacers here so that they could change the distance away, because sometimes the sensor needs an exact distance away. So instead of having to change the whole 3D printed part every time, they can just change the length of these spacers. If they need to move it a little closer or move it a little bit further away, they can do that really easily. All right, what else do we have? So we'll look at that in just a second as we look at the hatch mechanism. I guess we'll do cargo first, then we'll look at hatch. So cargo is the balls, so they had to have a ball intake of some side, and they decided to make a pretty simple one. This section of the intake doesn't need to do a lot, so it doesn't have to like deploy at all. It's stationary, so they have this mounted plate here that's always attached in here. When they're able to start the match, they're able to start with this whole like mechanism up vertical, so that's how it's able to deploy outside of the frame perimeters by using the actual wrists to put this outside onto the ground. And then they have, where's the other, what am I looking for? Somewhere. Oh, there's the pulley. So yeah, so they have this motor gearbox here. It's another 775 into a Versaplanetary, and they have a little round belt pulley. So this is not a timing cord, so this is a little bit easier. Things could slip here and still be fine. So if this gets caught on something on the floor or something, it's fine. If this stops, the motor would keep spinning and the belt would just slip. So it's like a round belt that they're using to transfer power here. And so it can slip easily, which in this case is probably good. It's also really compact. And so that's what they use to power this bottom roller. And then the top roller up here is powered through a timing belt, and when they need to, they can actually use these cylinders here to deploy it out. So this pushes out and gets on top of the ball, so they can suck it in and bring it onto this lower roller. It's a little weird because these are on two different sides of the ball and they're going the same direction. Oh, no, I know what they did. So it's not in CAD, but because it's a round belt and not a timing belt, one of the compact things it can do is if you need to get this to reverse, which they would if they wanted this to also be sucking in, right? They would want this to be rotating from this picture clockwise, and they would want this roller to be rotating counterclockwise to bring it in. What they do is they do a figure 8. So instead of having a normal loop like you would with a normal belt or with a chain or anything connecting these two rollers, you can actually go up with a figure 8 and have the belt basically cross itself in the middle, and now this roller is going to be backwards from the top roller. So that's going to let them suck in the ball from both below and at top without having to do any other complicated mechanism to get that reversal. So a lot of times if we're doing reversal like we did on the hood rollers we have for our launcher, we used gears to do that because we wanted that to make sure it was going to not slip at all. We wanted to make sure we were transferring a lot of energy back to those rollers, and that even if it jammed up, it was still spinning. If you have a case where you don't necessarily care as much if it jams, you can use a round belt like that, do the figure 8, and it works. So our 2020 robot has a setup like this on one of the rollers that we needed to do the invert on. We didn't have a lot of space, so we did the figure 8 belt technique to do the same thing that they did here to get that reversal of direction. What else do we have? So a couple other things. So these plates, these orange plates, are almost certainly polycarbonate. So these are just plastic. We would just cut these on our laser. But anytime where they have some of the shafts going through with the actual bearings in here, so this is a hex shaft going all the way through these rollers, and on the ends, they put these little aluminum plates that then they'll either bolt or rivet into place, and that just helps support the load that gets placed on here, so you don't crack the plastic as easily, which is definitely a thing that can happen. It happened to our intake plates a couple times where we didn't have some metal reinforcements in there. So that may be a thing we want to do on our intake, is to reinforce some of the joints and where things are mounted with some pieces of aluminum, spread some of the load out on the plastic, and you'll get less of those cracks and damaging where we have to replace those plates pretty regularly, especially under some impacts and things as well. This also, actually the way they did this, I take that back. They did not just use these as support. I didn't realize the way these were mounted. These are actually there to retain the bearing as well. So this doesn't support in the same way. So yeah, other teams have done it the other way where you do support. These are actually, because of the way they CAD'd them, these are here to retain the bearing. So if we look at the bearing itself, they have a flange. So this outer flange here is just pressed into the hole in the polycarbonate that is this normal outer diameter. And if you just did that, it's very possible for the plate to want to go either to the inside or for the bearing to pop out of the plate, and you don't want that to happen. So they put these plates on the outside that actually cover the flange. Let me see if I can get a click on the flange somewhere. So yeah, so you can see it here. So they cover the flange of the bearing, and then they bolt in or rivet in to here, and that way the bearing and the plate can't separate until you actually remove this plate. So if they need to change the bearing for some reason, they have to take this plate off to do it, so it holds everything together a little bit stiffer, and under any impact or anything, you're not gonna have these bearings popping out. So it's a bearing retention plate, not necessarily something to actually hold up the bearing itself, but you could add another one. You could do something on the backside to support the bearing. Just kind of depends on what you're doing, especially if you use a thinner piece of polycarb or plastic here. You may want a retention plate and a support plate. It just kind of depends on how you're doing your design. Okay, I think that's most of it. Yeah, and then the other part, I guess, of the ball mechanism is this back bar. So as the intake is coming in, this is what stops the ball from just going past everything and actually is able to get held in. So you have this lower point, this upper point when it's folded out, and this back bar sort of make a triangle around the ball and hold it into a known location so they're able to score it. My guess is this little 3D printed part here is to hold some type of bump sensor so that they can sense when they've actually fully intaked a ball. That sensor's not in CAD, so I don't know exactly which one they were using or what they were using here. But it's very possible, like just because this has like zip tie spots and a little bit for where a wire would come out, there's probably some sensor that's in here that as the ball came in, it either touched it or this was able to see from like a distance where it saw something got really close to it, and then they would know a ball was in their mechanism and ready to score. Okay, the other mechanism, because 2019 was a double game piece game, is their hatch mechanism. So in here they have two little cylinders, so this is all pneumatic. A lot of teams' hatch mechanisms were all pneumatic. So they have two cylinders here and a larger cylinder here. And so to actually grab the hatch from the loading station, they would drive in, they would push these in, these little tabs, these would go in, and this disc from above, let's see what that looks like. So from above, these would come inside, and so you just have this like cone, or this little triangle wedge shape that would go into the center. They actually have a little roller right here at the front, so if they missed, they could like slide it in and get it into the center, and drive this into the center pretty hard. And then once they were fully in and the hatch was basically touching these back spots, they would retract these cylinders like they are now, and they would swing out, and now a portion of the hatch would be sitting right here and on this, and this little thing would be in front of it so that the hatch couldn't fall off anymore, because now this is bigger. The distance from here to here was bigger than the inside circle of the hatch. So now the hatch can't fall off. Since this is bigger than it, there's no way for it to slide out and get through that circle at all. And so that worked well. This is all protected in behind these like big pieces of polycarbonate, and pretty lightweight. You have these tiny cylinders, not a lot of moving parts, just these single joints out here. Again, some cool use of 3D printed parts to be able to make these pivots, act as spacers, and kind of join everything together. Yeah, and then some more. This is probably 3D printed as well, just to space off the whole plate. And then in addition to that, they have the actual sliding element that's able to push this whole hatch mechanism against the rocket when they want to, or against the scoring location when they want to score the hatch. So this out here, when it's extended, is connected in between these spacers with a bolt. When they retract it and they bring this rod in, and they take it from here, this whole assembly can slide out however long this is, 4 or 5 inches. Yeah, probably 4, something like that based on my eyeballs. Somewhere in that neighborhood. It's probably about the distance from here to here as well. Let's see where we're at, because they probably don't want this to go too far into there. Yeah, so distance, yeah, 4.25, so it's probably 4 inches. And so this lets them push the hatch actually on there and secure it very well. So even if they're off at a little bit of a distance, they don't quite get in the same spot, they can push it in. And I believe this whole thing can pivot. Yeah, so the way this works, this pivot right here is set up so that when it's retracted back, this whole thing gets flat, because it pushes up against this block here. And then they also have these 2 other little sheet metal pieces for the hatch that allow it to keep the hatch straight when it's fully retracted. And then when they push out, this whole assembly is able to pivot on this center post. So even if they're at a weird angle and they push out, it's able to change angles to be off a little bit, and they can angle the hatch to actually still stick on and score. So there's a lot of little details into a mechanism like this that isn't actually that much stuff. It's a tube, some 3D printed stuff, a couple pneumatics, but if you do the design right, you can get it to be incredibly effective at whatever the game option is, whatever new unique scoring task we have next year. They thought through a lot of potential problems with it, and were able to find a solution that worked very well for them. Lots of little things like the gap up here. It's possible some of this is for springs or for hard stops. We don't entirely know because not everything's mounted. We could probably look through photos and probably find a little bit more. Some more things that are 3D printed, so another good use of 3D printed parts. Okay, so yeah, another good use of 3D printed parts here, where you could get this printed to have this tube slide in and out through this. Is probably a plastic 2x1, I'm guessing. So they have a polycarbonate tube here to keep weight down and allow it to slide pretty easily. So there's a lot of little details in there that you have to play with. So like exactly like what the gaps are on all of these to make sure it can slide but not bind. So yeah, so this is like a 0.1 distance or 0.01. So yeah, so that's pretty tiny, but it's probably 0.01 all the way around, and they probably found that that works well enough. But with something like 3D printed, you could just print another one. If it ends up being not right, you could design it, add a little bit more of a gap, tolerance a little bit differently, and get it to slide the way you want it to. Okay, it's already 9, so I'm going to quickly go through the end game so we can be done in the next 10-15 minutes. So the end game mechanism is into basically 2 parts. You have the part that actually mounted on the first moving stage of the elevator down here. And again, most of the time during the match, this is all folded up and out of the way like it is shown here. I don't think this has a version that lets us see it unfolded, but we can go back and look at the video. But you basically have these leg segments that pop out. So we have this leg, and this main plate. And so these all are pivoted out here on this setup here. Did I select the right ones? No, I selected the wrong ones. These are pivoted out. Yeah, these are pivoted out the back. There we go. Okay, so these are pivoted out the back. These are the wheels that are mounted on it. And these pivot out and come out this side. So these long tubes, when they actually go to deploy them for the end game, they'll raise the whole elevator up. These will pivot out to where they're going to stick out the back. And then the front pivots the other way. So this bar here is a 4-bar. So we have a linkage in place to allow this tube with these like rollers on it to be able to deploy out and go to the top of the hab. And that's what actually does. That's what actually pulls them on to the hab. So you have this motor here that's spinning this whole shaft, and it's going to put these rollers directly onto the hab surface. And so as they deploy up and lift themselves completely off the ground, these spin and drive them forward. So they're not using their drivetrain until they get their drivetrain fully on the platform. Most of the time they're dragging themselves forward with this roller right here. So they have a motor into a gear reduction, belt and pulley, a lot more 3D printed parts. This is almost certainly 3D printed too. With all the gear teeth and stuff, it'd be really hard to manufacture this any other way. And that's what mounts them, or that's what lets them do that pull method there. And we have a few more pneumatics in place to actually deploy the leg assemblies and this 4-bar. So they have a pneumatic here that they push out to unleash it. So they push this lever out. Right, so they have this little latch here that goes over this bar. When they extend this cylinder, it opens up. This is able to now move up. They have some springs in place that spring it forward. So these are modeled in CAD. These right here are called torsion springs or rotary springs sometimes. We use them a lot. We probably use them more than almost any other FRC team. And they're very helpful in counterbalancing things, doing other things. I'm not entirely sure which pins they're mounted on in this specific case, but in some way, somehow this spring is probably putting force, probably here, somewhere like that, to want to drive this forward. So as soon as that is released, the spring is pushing up on this, and it's going to rotate this whole arm, which in turn is going to rotate this arm, and it's going to drive that whole assembly forward. And then once the elevator actually starts pushing down, because of the 4-bar geometry, it's not going to be able to want to go backwards, and they're able to put a lot of the downforce from actually lifting their robot into these wheels here, so they get a lot of traction and they can drive themselves forward, and they don't have to do they don't have to like use the pneumatics to try to push down or hold the element out there without it folding back up. It's all done through the geometry of this linkage, so that when they actually, once it's folded out, if you try to just push it up from the bottom, it's not going to want to fold back. And then for the back legs, I'm not entirely sure how they unlatch those. Oh, they get unlatched at the same time. So we can see it here. So as soon as they unlatch this front mechanism and this arm starts pivoting forward, you now have it come out of this little crevice in the back legs, and those are going to spring down as well from both sides. So just with those two little pneumatics there, they're able to deploy both of those two sets of legs that they need deployed very easily, because they just have latches in there to do that. It's very likely that there's some form of spring or surgical tubing or something else that are pulling back on this bar, probably, something like that. I don't know if there's anything else in CAD that's going to give that away. But somewhere on the other side of this pivot, there's probably a spring that's pulling back to here, so that as soon as that little latch is done, these want to fold down and come out to the back side. Okay, so that's how that works. And then when they want to climb, they actually just reverse the elevator, put it in low gear, and they can push themselves up. To pick up the other two robots, they built in these basically little platforms that fold off the side of their robot. These need to be really lightweight but really stiff. So these are almost certainly carbon fiber tubes, so that they can be light but still stay very, very stiff, so you're not going to bend them by putting a robot on top of them. Any like piece of aluminum this same size is probably going to bend over time and be quite a bit heavier. So it's possible they use something else, but my guess is carbon fiber. Most time with carbon fiber, you're not going to want to actually screw into it, so a lot of times you clamp it, or you put it in and epoxy it. So this hole right here where it's blind, it's very possible that they epoxied this into the hole. You don't see any screw holes or anything for that reason, because you normally don't want to actually puncture a carbon fiber tube when you're mounting it. So most of the time you're going to clamp across it, where you have a couple plates and bolts and you're securing it just with clamping force, or you secure it with epoxy. So here's a place where they clamp it. So you have the tubes going through here, you have a bolt crossing that hole, and as you bolt down that middle, these squeeze in and you clamp the tube there. Okay, so these are able to fold down because we have the pivots down here really low. So these are mounted through that shaft going right through here. These big blocks are 3D printed. You have some metal reinforcement plates, most likely. We can see what the plate looks like, these big blocks right here. So yeah, so these are printed. A lot of times, like giveaways, you have this nice flat surface that you'd be able to print it on. And then you have that complex geometry that you wouldn't want to make any other way. Not easily, it would be a lot of wasted material to mill this out, but it's doable. So it's possible they made a version of aluminum at some point, but if they could get away with something this thick out of onyx or something like that off of Mark IVs, it's probably what they did. Yeah, so then this is a rather simple mechanism. All they do is have let me see where it is. There's the spool. They have a motor and a big gearbox that has a lot of reduction in it. They have a little extended shaft here, so we would probably use a max planetary for something like this, because we can have the output shaft go however long we need. They have a tiny gear to a bigger gear, so they get a little bit more gear reduction. And then they have a spool here, and so they just have a string that wraps around this spool. They probably connect it to this bar somehow. And then when necessary, they can unspool it. This whole, the platform falls down. Once the robots drive on, they can re-spool, so they can actually like tilt the robots into themselves so they're not going to fall off, or this thing isn't going to go any further down, and they can put all the load from this platform. They can support a lot of it by that string instead of by the lower joint. And then they're able to do the full lift. So when we actually see it do the lift in that video, we can see it a little bit easier how that mechanism actually works. Yep. Oh, so they spring up, so they actually have it going up over a pulley a little bit here. I don't know if that was their final version. They still have the spool there. The string goes up a little bit further and down. Yep, and then they get that all tilted up. They have the rear legs already sprung out. The front wheels pushed out as well. Yeah, so you can see those front wheels there, and everything just gets driven right on. Yeah, they never use their drivetrain. They don't put the drivetrain back down until the end. This was pretty early. This was their reveal night stuff, so a lot of this probably changed and the CAD's been updated, so some of this is probably different by the time they actually got there, by the time the season was wrapping up and they released the CAD. But you can see a lot of that's built into there. Okay. I took a little bit more time than normal, but that is it for tonight.